The supplemental practice or homework problems for Chapter 6 start with an amortization table with a $180,000 beginning balance with 5 annual payments at an 8% rate. To construct the amortization table, let me first calculate the payment amount on this loan by making 5 annual payments at an 8% rate and borrowing the $180,000 today, which is a positive present value. When I compute the payment, of course, the calculator will put a negative sign in front of it, and there is no lump sum future value in this case. So the 5 equal payments to repay my $180,000 loan at 8% interest would be $45,082.16. That payment amount in a fully amortized loan like this, the payment amount will be constant the whole way down the payment column here. So let me go ahead and put in $45,082.16 to be my payment amount during each of the 5 years. Now the first line of the amortization table, I'll take the $180,000, I'll add the interest that I charge and subtract the payment. So the interest here will be calculated on the beginning balance in each row. It will be, since this is an annual loan, 8% of that beginning balance. So 8% times the beginning balance in the first row there, 8% of the $180,000 loan amount means interest charge will be $14,400, which will be added on to that beginning balance, and then my first payment will be subtracted off. So before I make the first payment, I owe $180,000 plus $14,400 interest. I owe $194,400. Let me subtract my $45,082.16 payment, and once I make that payment, then I will owe $149,317.84, which is my beginning balance in my second line after that first payment was made. So in the second row of the amortization table, my 8% interest will be multiplied by the new balance, $149,317.84. So the interest charged in row 2 is $11,945.43. That is added on to this $149,317.84 balance, and then my $45,082.16 payment is subtracted off. So after that payment is made, I owe $116,181.11. That becomes my beginning balance for my third row of my amortization table. The 8% interest net rate is now multiplied by the $116,181.11. So the interest charged on this third row is $92.94.49. You can see the interest amount is becoming smaller and smaller. When that's added on to the $116,181.11 beginning balance, and then my $45,082.16 payment comes off, I owe $80,393.44, which is my beginning balance for my fourth row of my amortization table. I've got the loan down to $80,393, and 44 cents. So I multiply the 8% interest rate, and now the interest is 64, 31, and 48 cents. Add it on to my $80,393.44 balance, and I'll take off my $45,082.16 payment. My loan balance is down to $41,742 and 76 cents. %8 interest is charged on that balance, so the interest in this fifth row is $33,39.42 added on to the $41,742.76 balance. And when my $45,082.16 payment is taken off, I have actually paid 2 pennies more than I needed to. That's because I'm rounding every item in here to the nearest penny. Thus, there's a rounding error that produces that 2% error. So as you notice, the amount of interest charged each period becomes smaller and smaller. You'll also notice that the balance here, ending balance, is going down faster and faster. That's because my payment amount is constant and the amount of interest charged becomes smaller and smaller, so each payment takes a bigger chunk off of my balance as the loan gets paid down. So in this first row, I reduced the principal from 180 down to a little below 150, so the principal reduction was a little more than $30,000 in the first row. The last row, obviously, the principal reduction is from $41,700 basically down to 0, so the principal reduction was quite large. This final payment included relatively little interest and was mostly principal reduction. In Part B, it asks for us to total the interest column. So take the $14,400 interest from the first row there and add on the $11,945 and 43 cents and the $92.94.49 plus the $64.31.48 plus the $33.39.42, and I see the total interest column was $45,410.81. Notice I made 5 payments and they were all the same. So in Part C, it says total the payment column. Well, that would be 5 times that level payment amount of $45,082.16. So 5 times the $45,082.16 means the total of the payments was $225,410.80. If I subtract that beginning loan balance of $180,000, then I get $45,410.80. Total up all the payments here. 5 times that payment amount totals the payments $225,410.80. Subtract the $180,000 beginning loan balance. Obviously, anything I paid back must have been interest, so $45,410.80 was interest that I paid. The total I repaid minus the amount I borrowed must be the total interest on the loan, which is exactly the same that I get if I total the interest column above. In Part D, it says, what is the balance after the first payment if the loan payments above were made monthly? So, in other words, set up an amortization table, but just do the first line using monthly payments. So the first thing I need to do here is to calculate what the payment would be if the loan were repaid on a monthly basis. I'm going to still be borrowing $180,000, but I'll repay it monthly over the 5 years, so that will be 60 months. I'll take my 8% rate and divide it by 12 to get 2/3 of a percent per month as my monthly rate. And the payment amount, of course, the calculator will put a minus sign in front of it. I will compute my payment amount. So clear the calculator, and now with monthly payments, N is 60, which is months. Take 8, divide 12, and you get 2/3 as your IY, which is percent per month. Your present value of $180,000 then results in a payment of $36.4975. And I'm supposed to calculate the balance after the first monthly payment is made. So with a $180,000 beginning loan balance, I would add interest. It would not be 8% of the loan, it would only be the monthly rate, so it would be 8% divided by 12. So I'll take that 0.08, divide by 12, and multiply by my $180,000 beginning balance there. So the 8% for the year, 0.08, divided by 12 will give me my monthly rate that I multiply by the $180,000. So the interest charged that first month would be $1,200. And then my first $36.4975 payment would come off. So before I make that first payment, I owe the $180,000 I borrowed plus the $1,200 interest, so $181,200. Subtract the $36.49.75 payment, and that results in my balance after the first payment is made of $177,550 and 25 cents. So if the loan were done monthly, I have to calculate a monthly payment. I also have to remember to only add 1 month's worth of interest, not a full year's worth of interest. In problem 6.2, we're supposed to calculate the effective annual rate for different compounding frequencies for a 7% APR. For annual compounding, there's one compounding period per year. So our periodic rate, which is our APR, divided by the number of compound periods we have per year, is 7%, the same as our APR. There is no difference between the APR and the effective rate when the compound frequency is annual. But we'll follow the formula here. It says take 1 plus our periodic rate, raise it to the number of periods per year, and take the 1 off. And so we see our effective annual rate is 7%. In part B, we're supposed to calculate the effective rate under semi-annual compounding. I'll take my 7% APR and divide by the number of compounds per year, which for semi-annual compounding is 2, and I'll get a periodic rate of 3%. I'll take 1 plus that 3.5% semi-annual rate, compound it 2 times during the year, and take the 1 off. So remember the exponent key on the calculator. The y to the x key is right above the number 9. So let me enter the 1.035, y to the x 2 to raise to the second power, and I get 1.071225. I'll take the 1 off, and that gives me 0.071225, or 7.12% as my effective annual rate. In row C, for quarterly compounding, I'll take my 7% APR and divide by my 4 periods per year to get 1.75% as my quarterly rate, or 0.0175 as a decimal. To calculate the effective rate, I'll take 1 plus this quarterly rate and compound it 4 times during the year and take the 1 off, and I get 7.19% for my effective rate for 7% APR compounded quarterly. For my monthly rate, I'll take my 7% APR and divide by 12 because there are 12 months in a year. So when I take the 0.07 and divide by 12, I get a monthly rate as a decimal of 0.00583 repeating, which is almost 0.6% per month. Take 1.005833, compound that out 12 times during the year, and then take the 1 off, and you get 7.23% effective rate for a 7% APR compounded monthly. For daily compounding, I'll take my 7% APR and divide by 365 days in a year to get a periodic rate of 0.000191781. If I add my 1 to that, I'll get 1.000191781, which I will compound 365 times during the year and then take the 1 off. That gives me 7.25% effective rate. So you can see as the compounding frequency goes from 1 to 2 to 4 to 12 to 365 times per year, my effective rate goes from 7 to 7.1225 to 7.19, 7.23, and finally, with daily compounding, the effective rate is 7.25%. Now it asks us to verify these parts above using the interest conversion feature on our calculator. NOM is our APR. It's 7. The calculator knows that's 7%. Let's verify it for daily compounding. So our compounds per year would be 365, and then I'll compute our effective rate. The interest conversion feature on the calculator, since it says ICONV right above the number 2, I'll press second 2. When it asks me for NOM, I'll put in 7 for my APR, and I have to enter it. Remember the enter key, and then up arrow, C/Y is compounds per year, 365, enter, and then I go up to effective and I press compute, and I get 7.25% effective rate based upon the 7% APR and daily compounding. So a 7% APR, which is what the calculator calls the nominal rate, with 365 compounds per year, does produce a 7.25% effective annual rate. So we're asked to verify the results here using the interest conversion feature on our calculator for annual, semi-annual, quarterly, monthly, daily compounding. Remember, interest conversion is right above the number 2, so second 2 will access interest conversion. In this case, I have a 7% nominal or APR rate, so I will enter 7 for nominal. I'll up arrow to the compounding periods per year, and for annual, which was the first example, I'll put in a 1, enter that, go up to effective, and I need to compute, and I get 7% for my effective rate. Go back down. It was a 7% APR with annual compounding, and the effective rate is the same as the APR when compounding is once per year. If I go back down and overwrite the CY for 2 compounds per year for semi-annual and enter that and go back up to effective, I need to recompute, and I get 7.1225 effective rate for the 7% APR compounded semi-annually. Of course, I go back down, and for quarterly, I'll put in 4 and enter it for CY. Go back up and recompute, 7.186%. So 7.19, I believe we rounded that too. Go back down and put in 12 for monthly. I have to enter it each time, go back to effective and recompute and get 7.23. And finally, for daily compounding, go back up and recompute, 7.25. Since I happen to know there are 525,600 minutes in a year, for daily compounding the rate would be a little higher yet. And that's just about as high as it gets. It's about 7.25% for a 7% APR, no matter how frequently you compound it. In Part 6.3, it asks us to calculate the future value of $10,000 invested at 7% APR compounded monthly for 5 years using the following, and we should get the same answer in Parts A and B. It says in Part A, use the number of months and the monthly rate, 60 months, and 7% APR, 7 divided 12 is 0.58333333%. We invest $10,000 today, and we're going to compute our future value. There is no payment. So don't forget, second, clear TVM to clear your calculator. 60 in, take 7 divided 12 equals, and then press IY, and then your 10,000 negative PV. You can compute your future value, 14,176 and 25 cents. In Part B, it says use the true effective annual rate that you calculated for the monthly compounding that you calculated in Part 2D above. So use this 7.23% true effective rate that you calculated along with the number of years now. So for N, if N is 5 years, and IY is that 7.23% effective rate we calculated above in Part D of 6.2, Part D for monthly compounding, then it is a 7.23% rate per year. So for my $10,000 investment, of course no payment, I can calculate the future value. So second clear TVM, 5 in, and then 7.23 IY, my 10,000 negative present value, my computed future value is 14,176 and 90 cents. There is a difference of some 65 cents here, but that's rounding because this 7.23% rate was rounded. It had a lot of decimal points I rounded off. So being off by 65 cents on a $10,000 investment is just a rounding error. But you can see what the effective rate does. If I use 60 months and the true monthly rate here, percent per month, I get the future value. Or I can use the number of years and that effective rate per year that reflected the monthly compounding, and that gave me 7.23%. When it reflects the monthly compounding, I get the same result. In Part 6.4, it says you invest $10,000 today. What is the future value in 1 year if the investment earns 9% APR compounded monthly? Well, 1 year with monthly compounding is 12 months. I'll take my 9% APR and divide it by 12 to get a monthly rate of 3/4 of 1% per month. I invest $10,000 today, and there's no payment. I will compute the future value, So don't forget second clear TVM. Take the 12 months, 12 in. 9 divided 12 is 0.75 IY. And 10,000 negative PV. That will grow into 10, 938, and 7 cents. Part B says, what is the percentage increase in the value of this investment over the year? I end up with 10, 938, and 7 cents. I started the year with 10,000. So my investment increased by 938.07 on a $10,000 investment. So that is a 9.38% return over the year. That is what I effectively earned. I have 9.38% more dollars 1 year later. So for this 9% APR compounded monthly, I could see it really earned me 9.38%. That must be the effective rate for a 9% APR compounded monthly. Check it out. Second 2. And let's put in that 9% APR as our nominal rate, which we need to enter. And then we use the up and down arrow keys to move between the different fields. So let's go up to compounds per year. And since this was a 9% APR compounded monthly, there would be 12 compounding periods in the year. I go up to effective and compute, and we see we get the 9.38% effective rate, which is what we got for 6.4 Part B when we calculated the percentage change for the year. So that is what we're truly earning over 1 year's time if we earn a 9% APR, but it is compounded monthly. Problem 6-5 says Fred's bank will loan you $28,000 for 5 years to buy a car. The loan must be repaid in equal monthly payments, and the annual interest rate is 7.2% on the loan. Since the payments are made monthly, we always assume that interest is charged with the same frequency as the payments, so this 7.2% APR will reflect monthly compounding. So we're going to do everything on a monthly basis. With the 5-year loan, monthly, there will be 60 monthly payments, so in will be 60. We take the 7.2% APR and divide it by 12 to get a monthly rate, which is 0.6 or 0.6% per month. We borrowed $28,000 up front, so that's our present value. There is no single lump sum future value involved, so we're just going to compute the payment, which will be a monthly payment because we've put in the number of months, the rate per month. The payment will be the payment per month, and the payment amount is $557.08. If you put in a positive present value there, the calculator will actually put a minus sign in front of that payment, meaning you have to pay out the $557.08 each month for 60 months to pay the loan down to 0. Problem 6.6 says if you want to have $3 million at retirement in 45 years, how much must you put in a retirement savings account each month? Well, the payments will be made monthly, interest will be earned monthly, so this 8.4% APR will be compounded monthly, so we're going to do everything on a monthly basis. 45 years on a monthly basis is 540 months. Take the 45 years times 12 months per year, and you get 540 months. Take the 8.4% APR and divide it by 12, and you get 0.7 or 0.7% per month as your monthly rate. You want to accumulate $3 million at the time you retire, 540 months from now. So when you compute the payment, it will give you the monthly payment that's necessary to accumulate the $3 million 45 years or 540 months from now. And that payment is $497.13. The calculator will put a minus sign in front of that, meaning you have to pay that out each month for 540 months to accumulate the $3 million. Problem 6.7 says you wish to borrow $25,000 to be repaid in monthly installments of $400 beginning 1 month from now. That makes it an ordinary annuity because the first payment is not made today. The first payment is made at the end of the first month, 1 month from now. This will take place over 10 years. You're supposed to calculate the APR, or the annual percentage rate. So with 10 years in monthly payments, that's 120 months. You borrowed $25,000 today, that's a positive present value, and the payment is something you pay out, so that's negative $400. Everything is monthly, so when you compute the IY, you'll be calculating rate or percent per month, which you'll multiply by 12 to get an APR. So the monthly rate is 1.2318% per month, multiply by 12, and the APR is 14.78%. Problem 6.8 says if you invest $500 every 6 months at 8% APR, with the first deposit being made 6 months from now, which makes it an ordinary annuity, you don't make the first payment today, you make it 6 months from now, how much would you accumulate at the end of 10 years? Everything will be done on a semi-annual basis, so you have the $500 payment, that's a negative payment, 8% APR, on a semi-annual basis, that's 4% per semi-annual because it's 8% per year, 8% APR. It's 1/2 of that, or 4% per semi-annual period. You want to calculate or compute the future value at the end of 10 years. With 2 semi-annual periods per year, that is 20 semi-annual periods. So the future value is $14,889.04. You put a minus in front of the payment because you pay that out, and the calculator will put a positive 14,889 as the solution. Problem 6.9 says you just won the lottery and you will receive $2.5 million per year for the next 20 years. While the Lottery Commission will call this a $50 million jackpot because they simply take the $2.5 million per year and multiply by the 20 years, they will not give you $50 million, and you will not use $50 million to solve this problem. You will use the $2.5 million payments and the fact that there are 20 of those payments. So the question is, what would your lump sum payoff be if you selected the cash option? That means they will give you the present value of the annuity, the present value of the 20 payments of $2.5 million, and because of time value of money, that would be significantly less than the $50 million advertised. They will discount all those annuity payments at 8% per year to calculate the cash option or the present value of that ordinary annuity. So everything is annual. There are 20 annual payments discounted at 8% per year. Each payment is $2.5 million, and we're going to compute the present value. You may choose to put a minus sign in front of that payment because you're going to give up the payments to get this lump sum present value of $24,545,369. If you put a minus sign in front of the payment, the calculator will give you a positive present value. If you don't put a minus sign there, it will put one in front of that present value. If the first payment were actually received today and the 20th payment were received 19 years from today, this would be an annuity due, and the entire cash option would be worth 8% more. In other words, you get one more period worth of interest if the payments come at the beginning of the period. So if this were an annuity due with the first payment today, we would increase this payoff by 8%. It would be worth 8% more, or a total of $26,508,999. Payments come 1 year sooner. Each payment is worth 8% more. So the total value of the annuity is 8% larger. Problem 6.10 says, which of the following accurately relate the present value and future value, respectively, of ordinary annuities with annuities due? Well, the annuity due is always worth more than an otherwise identical ordinary annuity, whether it's a present value or a future value. The payments come sooner, so for a present value, you get the money sooner, it's worth 1 period more interest. For a future value, the annuity due is worth more because you invest the money sooner and it will earn 1 period more interest. So in each case, the annuity due is going to be worth more than the otherwise identical ordinary annuity, and that is choice C. The present value of the annuity due is greater than the ordinary annuity. The future value of the annuity due is greater than the ordinary annuity. Problem 611 says the MSU Department of Intercollegiate Athletics purchases a jet for $2 million to fly the teams to various locales. The interest rate on the loan is 8% and requires 6 equal annual payments. What is the balance of the loan after the first payment is made? To do this, we basically need to set up the first line of an amortization table, but first we will need the payment amount. We borrow $2 million, make 6 equal annual payments at an 8% annual interest rate, and the payment to pay off the loan would be $432,630.77. To calculate the balance on the loan after the first payment is made, we'll take the $2 million we borrow, add 8% interest for the first year, and then take off this payment that is made. So before we make the first payment, we owe the $2 million plus the 1 year's interest of $160,000. So before we make the first payment, we owe $2,160,000. When that payment comes off, then the balance is paid down to $1,727,369. It's often said that this payment includes principal reduction plus interest, so it might seem strange that we have to add on the $160,000 if this payment, quote, includes principal reduction plus interest. But that principal reduction and interest payment will not be applied until the interest has been added on to the loan balance. So you start out owing $2 million, you accrue $160,000 in interest, and then the payment comes off and the balance is paid down to that amount. Problem 612 says you've contracted to buy a house and borrow $300,000 on it, taking out a fully amortizing loan for that amount at a 9% APR for 30 years with monthly payments. What is the balance of the loan after the first payment is made? In this case, everything has to be done on a monthly basis. First, we'll compute the monthly payment, then we'll set up the first line of the amortization table to calculate the balance after the first payment is made. So for a 30-year mortgage with monthly payments, there will be 360 monthly payments. The 9% rate, APR, to calculate the monthly rate, we divide by 12 and we get 0.75% per month. We borrowed $300,000 up front, then we compute the payment with a positive loan amount, then the payment will have the minus sign in front of it on the calculator. The payment will be $2413.87. The balance after the first payment would be $300,000 plus 1 month's interest minus the payment. So we owe $300,000 and the first month's interest will be 9% for the year, but only 1/12 of that for a month. So 9% of the loan then divided by 12 to get you a month's worth of interest would be $2,250 in interest that first month. And then the $2413.87 payment comes off. So the balance after the first payment is made has gone down $164. You made a $2,400 payment and you knocked $164 off your loan amount because almost all of the payment went toward interest. And that is true in the early months of a loan. Almost the entire payment goes to cover interest and there's very little principal reduction. As you pay the loan down, that reverses as the loan balance gets paid down. The amount of interest in each payment is much, much smaller and the principal goes down much faster. But after this first payment is made, you still owe $299,836.13. Part C says compute the total interest paid over the life of the loan. Instead of completing an entire amortization table and calculating the total of the interest column, let's just figure out how much we repay to pay off this loan, and everything beyond what we borrowed would have to be interest. So we make 360 payments of $2413.87. Anything in excess of the $300,000 we borrowed is interest. So the total we repay is $868,993.20. 360 payments of $2413.87 is $868,993.20. Take off the $300,000 that we borrowed, which is principal repayment, and that leaves interest being repaid of $568,993.20. Problem 613 says you have just purchased a share of preferred stock for $40. The preferred stock pays an annual dividend of $5.60 per share forever. What is the annual rate of return on your investment? If you make a $40 investment and you get a $5.60 return each and every year, then your annual return is the $5.60 return divided by the $40 investment, or 14% is your annual return. You get the $5.60 every year. That represents a 14% return on your $40 investment. In 614, it says the perpetuity provides an annual payment of $40 per year forever, and the discount rate is 4%, and now we're going to put a value on the perpetuity. So in 13 we were calculating the return. Here we're going to calculate how much we would be willing to pay to ensure that we get a 4% return. So to calculate the present value of a perpetuity, it's the payment amount divided by that discount rate as a decimal. So the $40 divided by 0.04 means you'd be willing to pay $1,000 to buy this perpetuity. If you require a 4% return, then your $1,000 investment would be earning the 4% return if you get the $40 interest payment every year. You get the $40 every year. That gives you a 4% return for each year on your $1,000 investment. Problem 615 says the EAR is always greater than the APR. True or false? That is actually false, because when compounding takes place on an annual basis, they are the same. When compounding occurs more often than annually, the effective rate is greater than the APR, but when compounding takes place on an annual basis, they are the same. Problem 616 says, what is the APR and the effective annual rate for an investment that provides 1% interest per month for 6 years? Well, the APR is pretty obvious, I'm sure. It's that monthly rate of 1% per month multiplied by the number of months per year. So we just take the 1% per month times 12 and we get a 12% APR. For the effective rate, we want to calculate what type of compound growth will actually take place over a year's time if we're earning 1% per month. So we basically create a future value factor for a year, and then we take the one that's used to compound back off. So calculate the monthly rate, which was given to be 1% per month, or take your APR 12% divided by 12 to get that 1% per month periodic rate. Take the 1% per month periodic rate, add a 1 to it, and compound out 12 times. That gives you the future value factor for a year. If you take the 1 back off, that gives you the interest earned per year. So the effective rate is 12.68% effective annual rate. As you'll recall, interest conversion on the calculator uses the ICONV function, which is right above the number 2. So second 2 gets you into the interest conversion. NOM is your APR, so you put in 12 and enter it, and then go up to the compounds per year, which is 12, and compute the effective rate. So to illustrate, second 2 gets us into interest conversion. We had an APR of 12, so 12 enter. We go up to the compounds per year, and with monthly compounding, that would be 12 compounds per year, which we have to enter. And we go up to effective. There might be some old data there until we press compute. And when we press compute, we get our effective annual rate of 12.683%. When you have the asterisk there, you know that this result has been computed, and it is consistent with the APR you put in as nominal and the number of compounds you put in for C/Y. So the effective rate is 12.683%. 617 says, what is the effective annual rate of 12% compounded monthly or compounded quarterly? The effective annual rate for monthly compounding takes 1 plus the monthly rate, which is this 12% APR, divided by 12 to get a monthly rate of 1%. So 1 plus the 1% monthly rate compounded out 12 times with the 1 taken back off is 12.68%, just like we saw in the previous problem. Now for the quarterly compounding, we take 1 plus the quarterly rate, which is the 12% APR divided by the 4 quarters per year. So we have 1 plus that 3% quarterly rate compounded out 4 times during the year with the 1 taken off, and that is 12.55%. You could use interest conversion, keeping the same 12% APR in there as your nominal, and put in the compounds per year as 12 for monthly, compute effective, and then change the compounds per year to 4 for quarterly and recompute effective. But make sure you recompute if you use interest conversion, otherwise the calculator will not update the result until you press compute. Problem 618 says, how much additional interest would a $100,000 investment earn over a 5-year period if it earned 7% APR compounded monthly as opposed to earning 7% APR compounded annually? Let's calculate the monthly result first, and then we can take the difference rather easily because this will produce the larger amount. For the monthly compounding over 5 years, that is 60 monthly compounding periods, the 7% APR divided by 12 gives us 0.5833333% per month. The $100,000 investment would grow into a future value of $141,762.53 with monthly compounding. The annual compounding will produce a smaller result because the compounding will not be as frequent. The effective rate you earn will not be as high. So to do everything on an annual basis, we use 5 years, 7% per year. The $100,000 investment will grow into $140,255.17 for the annual compounding. So you can eyeball that's a difference of over $1,500. In fact, you will earn $1,507 more interest if your investment compounds monthly as opposed to compounding annually. And that's just over 5 years. The difference is over $1,500 just because of the monthly compounding as opposed to the annual compounding. Problem 619 says you are considering a $150,000 loan with monthly payments. The interest rate on the 15-year loan will be 6.75% APR. Part A, we're supposed to calculate the total interest paid over the life of the loan. As we've done before, we'll calculate the payment. We'll total up all those monthly payments and subtract how much we borrowed, and that will give us the total interest paid over the life of the loan. So on a $150,000 loan, that is your present value. The 6.75% APR divided by 12 gives us a monthly rate of 0.5625% per month, and 15 years with 12 monthly payments per year is 180 months for the term of the loan on a monthly basis. So when we compute that monthly payment, we get $1,327.36. The calculator will put a minus sign in front of the payment if you put in the loan amount as positive. The total interest paid would be the 180 monthly payments of $1,327.36 minus the $150,000 you borrowed, which is a total interest of $88,924.80. In problem B, we're supposed to calculate the effective annual rate of the 15-year loan. You could take 1 plus that APR of 6.75% as a decimal, divided by 12 to get a monthly rate of a little over 0.5% per month. When you add the 1 to the monthly rate and compound it out 12 times, then you take the 1 back off, you get 6.96% effective rate. Or you can use interest conversion, putting in the 6.75 APR as your nominal and 12 compounds per year, compute the effective rate, and you should get 6.96% using interest conversion as well. Problem 620 says Charlie Spleen wants to retire in 30 years and he wants to receive an annuity of $15,000 a year for 20 years after retirement. Charlie wants to receive the first annuity payment at the end of the 31st year. So if you look as of the date of his retirement 30 years from now, that's an ordinary annuity. Go 30 years into the future when he retires and he gets the first retirement payment at the end a year later, that makes it an ordinary annuity as of his retirement date 30 years from now. Well, the question is not how much he needs to have when he retires, but how much he has to invest today. Although working backwards, the first step would be to determine how much he will need when he retires. when he retires, he wants to receive $15,000 annual payments for 20 years after retirement. So if we discount those at 8% per year, on the day he retires, his retirement account needs to have $147,272.21 in it so that it can provide him with 20 annual payments of $15,000 per year, assuming this amount continues to earn 8% per year. If you total the 20 payments of $15,000, he's going to get $300,000 of retirement payments, but he only needs to have about half that amount in the account when he retires because it will continue to earn 8%, and that lets him get 20 payments of $15,000. Now, the original question was how much must Charlie invest today? So to ensure that he has this amount in his retirement account when he retires 30 years from now, we'll discount that back 30 years at the 8%. So we'll consider this a future value. He needs to have that amount in his retirement account 30 years in the future. We discount 8% per year. He needs to invest $14,636 today so that he can get his $15,000 annual payments for 20 years after retirement. Again, he retires in 30 years. He needs to have that much in his retirement account. That continues to earn 8% per year and will provide him the 20 payments of $15,000 per year. Problem 621 says, what would you be willing to pay for the following investments if you require a 6% annual rate of return? Part A is called Hare Enterprises stock and provides you a $10,000 payment after 5 years and then a $5,000 payment after 10 years. Well, the value of any security equals the present value of the future cash flows you expect to get from that investment. So we can discount these future values individually, see what they're worth in present dollars, and the total investment will be worth the sum of those two present values. So the $10,000 payment to be received 5 years from now, discounted at 6% per year by itself, is worth $74.72.58. The $5,000 payment to be received 10 years from now, discounted at 6% per year by itself, is worth $27.91.97. The entire investment together is worth $10,264.55. Now, the Tortoise Technologies is a very similar investment. It provides you $5,000 after 5 years and $10,000 after 10 years. So the Hare Enterprises gave you more money sooner. Basically, $5,000 of these dollars have been shifted up here to be received after 5 years. So they both provide a total of $15,000 over time, but the Hare Enterprises gave you the $10,000 after 5 years and the $5,000 after 10 years. So it gave you more money sooner and thus must be worth more. The Tortoise Technologies, when you discount the $5,000 5 years at 6%, that payment by itself is worth $37.36.29. The $10,000 to be received 10 years from now, when you discount that at 6% per year by itself, it's worth $55.83.95. So the total investment together is worth $9,320.24. It's worth more in the Hare Enterprises stock because you get more money sooner than you do for the Tortoise Technology stock. So the Hare Enterprises was worth more than the Tortoise Technologies. Now Part C says, if you paid the respective amount that you computed for each investment above, what would your expected rate of return have been for each investment? Well, you valued each of those investments by discounting those cash flows 6% per year. So you would pay more for the Hare Enterprises stock, but it would still give you a 6% return because it gives you more money sooner than the Tortoise Technologies. You could buy the Tortoise Technologies investment a little more cheaply. It would still give you only a 6% rate of return because the Tortoise Technologies did not give you as much money as fast as Hare Enterprises stock. You had to wait a little longer to get some of the money under the Tortoise Technologies investment. So both provide you a 6% return because you valued both of them by discounting the future cash flows at 6% per year.